Good morning. Welcome to C++ Now. Thank you all for coming. This is a much bigger crowd than I expected since I'm up at the same time as Tony. Since this is a talk about C++ reflection, I will of course start by talking about command line option parsing. I'm sure everyone loves writing code like this. Our application has 4 possible command line options. We iterate through all the arguments, looking for each possible option and processing it. This is tedious and error-prone. If we change any of the options, code needs to be updated in multiple places. And this code here doesn't do any error checking. If we had just the basic error checking, enough to avoid a crash if the user types in garbage, it becomes even more tedious. But what if we could ditch all this repetitive boilerplate? Just define a struct that holds the values of all the options and have the code automatically fill in the values of that struct from the command line arguments. That's it. No writing out the code for individual options, no code for parsing the options, parsing the values of the options. Just some generic code that does it all as if by magic. That's what reflection can do for you. Keep this example in mind as we go through this presentation. I'll show you the magic behind the parse option function later on. Welcome to my presentation about C++ reflection, where I will explain what reflection is, go over the proposal that is working its way through the standards committee, and give some examples of how reflection can be useful. I am David Olsen, the lead engineer on the HPC C++ compiler team at NVIDIA, where I keep our compiler, NVC++, running smoothly on many of the largest supercomputers in the world. I was the driving force behind the NVC++ feature of running standard parallel algorithms on GPUs, and I am supporting NVIDIA's efforts to run upcoming standard features such as linear algebra and P2300 senders on GPUs. Before I overwhelm you with all the coding examples and proposal details, I should spend some time reflecting on what reflection is. Reflection comes in 2 parts, introspection and injection. We'll cover introspection first. This is probably what comes to mind first when you think of the word reflection in a programming context. Reflection is when a program looks at itself and observes its structure and how it is put together. In other words, the program can ask questions about itself, such as, what kind of type is this? Or, what are the public data members of this class? Or, where are the buffer overflow bugs in this code? Just kidding on the last one. The program looking at itself is an important part of the definition. A program asking questions about some other program is a static analysis tool, not reflection. Given that it is known as reflection, you would think that a mirror is a good analogy. But no, a mirror only shows the surface of what it is reflecting. A better analogy, in my opinion, is an X-ray. An X-ray lets you see not just the surface, but the interior structure. Reflection lets a program look at how it is put together, not just its external behavior. When asking questions about itself, the program works with reflection values, usually referred to as reflections. To get a reflection value that can be queried, there has to be some way to get from the world of code into the world of reflection. This is known as the reflection operator. In the X-ray example, the reflection operator is the X-ray machine. This is what converts a real-world object, in this case, your right leg, into a reflection value, namely the view of the bones inside your leg. The other side of reflection is code injection, also known as reflective metaprogramming. This is the opposite of introspection. The code injection is lumped together under the general term reflection, and it differs from other kinds of metaprogramming because the results of reflection queries are used to generate the code. I looked for a picture of a robot fixing itself to represent reflective metaprogramming, but I couldn't find a good one. So you'll have to settle for Escher's drawing of two hands drawing themselves. While introspection needs to have a reflection operator to go from the code world to the reflection world, code injection needs to do the opposite, going from the reflection world back to the code world. Every decent reflection scheme will have some way to do this, though it is usually not as simple as an operator. For reflection to be useful, there needs to be something unknown for the program to ask questions about. The unknown thing could be anything, but is usually a type. Or reflection queries usually start with an unknown type before moving on to other kinds of unknown things. It is important that the program does not know what that type is, but that the compiler does know. If the code knows what the type is, there's not much point in asking questions about it. If the compiler doesn't know what the type is, then the asking questions about the type won't result in any useful answers. If you have code that is working with unknown types, you usually have polymorphism of some sort. It could be compile-time polymorphism, such as C++ templates, or it could be runtime polymorphism, such as object-oriented programming and class hierarchies. Programming languages that don't have any polymorphism, such as C, don't have reflection, because there's no significant amounts of generic code operating on unknown types. An example of code using an unknown type at compile time is C++ templates. In the function template here at the end, the code inside the function doesn't know what type T is, but the compiler knows what T is once it has instantiated the template. You might point out that the code that calls the function probably knows what T is, but the code inside the function does not, which is the important thing. Code works with a type that is unknown at runtime in dynamically typed languages or in languages that support object-oriented programming, especially in languages such as Java that have a universal base class. So, compile time reflection does introspection on static types, and code injection causes different code to be generated by the compiler. It is a good match for statically typed languages with static polymorphism or generics, as it is referred to in most languages. Runtime reflection does introspection on the dynamic types of objects. It doesn't affect the code that the compiler generates, but instead causes different code to be executed at runtime based on the dynamic types of objects. It is a particularly good match for object-oriented languages with universal base classes. Spoiler alert, C++ will have compile time reflection. To help you understand how C++ reflection fits into the bigger picture, I want to quickly go over some other implementations of reflection. We'll start with Java. While I spent several years programming mostly in Java, that was a long time ago. My Java skills are quite rusty, so there are probably some mistakes in the following slides, but I think the overall concepts are correct. Java reflection is runtime only. Java reflection predates Java generics, so it is designed to work with Java's universal base class model. The reflection operator is the getClass method that every object has. It returns a reflection value of the type class with a capital C that reflects the dynamic runtime type of the object. Once you have the reflection of the class type, you can navigate around, with each kind of thing represented by a reflection value of a different type, such as method, constructor, field, and array. It's hard to talk about this verbally because the types of the reflection values have the same names as the things they are reflections of. There are just too many meanings of the word class in this context. Code injection in Java is also done at runtime. You can create a new object by calling the new instance method of reflection class constructor. You can call a member function that was found via reflection by calling the invoke method of the reflection class method. You can change the value of the data member in an existing object by calling the set method of class field. An API like this would be problematic in C++, but it works well enough in Java because everything is an object. So all these methods can accept and return objects. I will use this problem as my basic reflection example several times in the talk. So let me go over the problem statement in detail now. Assume that we have been sloppy in our API design, and we have created some containers with a size method and some with a length method. And we are too lazy to fix up all the containers to make their APIs consistent. So instead, we want to write a function that accepts any kind of object, checks if it has a method named size or length, call that method, and return the result. This is slideware meant to show the use of reflection so the error handling is minimal. This is the Java solution to the problem. We have a method named size or length that takes a single parameter of the universal base class type object. First, we use the reflection operator, the getClass method, to switch from the code world to the reflection world. Remember that getClass returns the reflection of the dynamic type of the given object, not a reflection of class object itself. Once we have a reflection of the class type, we can get that class's methods. We iterate through all the methods, looking for one named either size or length. If we find one with the right name, we call that method using Java's code injection operation of method.invoke. Method.invoke returns an object, so we have to convert that to an int before returning it to the caller. And we're done. Next, we'll look at reflection in C#. My C# skills are also rusty, so I offer the same caveats about the accuracy of these slides. C# is quite similar to Java. I should have picked a language with a programming model different enough that reflection is done differently, but I don't know any such language well enough to be at all comfortable presenting about it. C# reflection is runtime only and is designed to work with C#'s universal base class model, which is even more universal than Java's base class model. The reflection operator is the getType method that every object has. It returns a reflection value of type that reflects the dynamic runtime type of the object. Once you have the reflection of the class type, you can navigate around with each of the things represented by a reflection value of a different type, such as method info, constructor info, or field info. Code injection in C# is also done at runtime. You can create a new object by calling the create instance method of the reflection class activator. You can call a member function that was found by reflection by calling the invoke method of the reflection class method info. You can change the value of a data member in an existing object by calling the set value method on class field info or property info. But C# takes code injection one step further than Java. In Java, you can create new objects of a class using reflection, but the class type of the new object must have been compiled into the bytecode in one of the class files or jars that the application is running with. In C#, it is possible to create entirely new classes at runtime. It's not easy to do. It's complicated enough that I won't overwhelm you with an example. It requires emitting .NET bytecode so that you have to do the work that the compiler normally does. But it is possible. Keep this in mind as we go forward. Here's the C# solution for the size or length problem. It's almost exactly the same as the Java example, except that it is shorter because C# has more expressive statements. In this case, the range-based for loop. Again, we have a method named size or length that takes a parameter of any type. We call the C# reflection operator getType to move from the code world to the reflection world. We get all the members of that class type and iterate over them. If any of them are named size or length, we invoke that method using method info.invoke. Convert the result object to an int and return it. Done. Now let's look at C++. At how C++ currently implements reflection. Hint, not really. That's why there is a proposal, which we will eventually get to, that does reflection properly. There's a tiny bit of runtime reflection in C++ right now, emphasis on tiny. The type ID operator can get a type info object representing a type. It can even get a std type info for the dynamic type of an object in some cases. While this runtime information is very useful to the compiler, it is used to implement dynamic cast and exceptions. It is essentially useless to the end user. The only useful thing you can do with a type info object is get its name. I don't know of any plans or desires to expand the functionality of type ID or type info. It is a dead end in the quest for C++ reflection. Type traits are much more useful. They allow for compile time introspection of types. There are a lot of standard type traits. These are all the ones that I could find. But type traits only work on types and the properties that can be represented in the type system. You can't get the methods of something or even get the parent scope of a name. You can't ask questions about functions except for things that are in the function's type or that affect template argument deduction. Standard type traits allow for very limited manipulation of types, mostly just adding or removing consts, volatile, pointer, and references, removing array extents, or converting between signed and unsigned integral types. This isn't really reflective metaprogramming, because the metaprogramming isn't using reflection information. These are just things that the C++ type system and C++ templates can do. While type traits are extremely useful and a very good addition to the language in C++11, they are lousy at implementing reflection because they were never intended to be the reflection solution. Type traits and many other parts of template metaprogramming are an outgrowth of the magic of function template argument deduction that happens during overload resolution. For overloaded function templates to work well, the designers of C++ had to come up with very complicated and sophisticated rules for template argument deduction. These rules can also be used to resolve class template partial specialization, which is what type traits are built on top of. One last thing in current C++ that is not reflection, but is reflection adjacent, requires expressions. A requires expression makes it very easy to ask whether or not a chunk of code is semantically valid. Requires expressions can do a couple other things, but the primary purpose is to check for code validity. It was possible to do this before with template metaprogramming, but requires expressions make it so much easier. While you can view this as a kind of introspection of the code, it is more of a surface view, like a mirror, not a look inside like an X-ray. While requires expressions are not reflection, they can be used to solve our size or length problem. Again, we have a function named size or length that takes an argument of any type, but this time the type of the parameter is a template parameter rather than universal base class. Rather than iterating through all the member functions of T, instead, we check if calling the size member function with no arguments is valid code that returns an integral type. If it is valid, then we call it and return its result. Then we do the same for length. Because we don't have true reflection with code injection available, we can't just call whatever member function happens to meet whatever criteria we are looking for. We have to check each possible member function one at a time and call the member function directly. This scheme would break down entirely if we were looking for a member function whose name fit a certain pattern, or if we were looking for a member function with certain properties unrelated to the name. One last stop on our reflection survey. Proposals for standardizing reflection in C++ that were ultimately dropped. In the 2010s, there was a lot of work to get reflection into C++ using a compile time template metaprogramming approach. A reflection value was a nameless, unique type. To figure out what kind of reflection a type represented, you would check if the type satisfied one or more of a large number of concepts. The reflection operator was the keyword reflexper. Reflection queries were done via type-based template metafunctions. Because everything was type-based, reflection programming was done via type alias declarations, as seen here. Getting from the reflection world back to the code world was done with more template metafunctions. To get the type from a reflection of that type, use getReflectedType. If the reflection value represented a function member function variable with static storage duration or a non-static data member, then getPointer would be used to get a compile time pointer to the thing. The pointer would be a regular object pointer, a function pointer, or a pointer to member, depending on what was being reflected. This reflection effort made it as far as being a published TS, but the TS was never merged into the C++ standard. In the late teens, the standard committee decided that template metaprogramming is just too cumbersome, and that the constexpr functions make for a better API for reflection. So everyone shifted their efforts to a new reflection effort, which I will go over next. A Clang fork that implements the reflection TS is still available on Compiler Explorer, so I can give you a taste of what working reflection TS code looked like. We have a function named size or length that takes an object of any type. We transfer into the reflection world with the reflexpr keyword, then get the reflection of the entire set of public member functions of the class, which are represented as a single type. Because we are working with type lists, we need a recursive class template with a partial specialization in order to iterate over the types that reflect the member functions. The unpack sequence template metafunction passes the type list to our class template. Our class template checks if the current member function is named size or length. If so, use getPointer to get a pointer to the member function, and use the pointer to member function call syntax, which I expect many people aren't familiar with, to call that member function on the given object. From the complexity and verbosity of this code, I hope you can understand why there was some pushback against the reflection TS and a desire for something better. There were many committee papers that proposed and explored other ways of doing reflection. One of the most significant was P1240, Scalable Reflection in C++. The paradigm switched from template metaprogramming to const-eval functions. Reflection values were compile time values of an opaque type. A new system called splicers was invented to do the code injection. I won't go into detail about P1240 because many of the details were copied by the paper that it inspired. P2996, Reflection for C++26. This is the meat of the talk. This is the part you should pay attention to if you're interested in C++ reflection. All the background I have given wasn't strictly necessary, but hopefully it gives you a foundation to better understand P2996. This is the proposal that is currently working its way through the Standards Committee. Some past reflection proposals have suffered from being too big. The committee wasn't convinced that they could get all the details correct on the first go. And once a bad feature is in a released standard, it can be very hard to fix it. So the authors of P2996 have taken the approach of going for a minimum viable proposal. They hope that this proposal is the right size, big enough to be really useful, small enough that they can get it right, and open to extensions that will fill out the reflection functionality at a later time. Compared to P1240, P2996 has improved and expanded the introspection support, making that part very solid. On the reflective metaprogramming, or code injection side of things, support is scaled back somewhat from P1240 to avoid some thorny problems with splicers and packs. But it also has the start of taking code injection in a new direction with the define class function, which I will cover later. P2996 has been advanced out of the reflection study group. It was seen by the language evolution and library evolution working groups in Tokyo last month. This was an introductory session to get initial feedback. It will take more meetings to work through some of the issues and gain consensus. Making it into C++26 is by no means a given, but those involved think the chances are pretty good. On to the actual contents of the proposal. All reflection values have the type std meta info. Different reflection values are different compile time values of meta info, not different types. Meta info is an opaque scalar type that is only useful at compile time. While meta info objects can exist at runtime, there is nothing useful that you can do with them at runtime. All functions that work with meta info objects are const eval, which means they are compile time only. Why one type for all reflection values rather than different types for different kinds of things like in Java? Two reasons. First, the C++ language has changed in the past, and it will continue to change in the future. Reflection needs to represent the structure of the core language accurately. Reacting to language changes will be easier if the structure of the language is not encoded in the type system. Second, and I think more importantly, it is easier to represent a heterogeneous container, or a collection of mixed things. A list of template arguments can be stored in a vector of info, even if those template arguments are a mix of type template arguments, non-type template arguments, and template arguments. The reflection operator in this proposal, which is how you transition from the code world to the reflection world, is a prefix unary caret. The operand can be almost anything with a name, or a type, or a constant expression, or the global namespace. The result of the caret operator is always a compile time value of type std meta info, and is the reflection of the operand. So some examples of the caret operator. If you take the reflection of int, you get the reflection of the built-in type int. Caret std vector of int gets you a reflection of the type vector of int. But if you apply the caret to just std vector with no template arguments, you get a reflection of the template std vector. Caret of std string gets you a reflection of the type alias std string. Remember, string is an alias for basic string car traits car, allocator car. And so there are ways to get from the alias to the underlying type. But caret std string will get you the reflection of the alias itself. Caret of a double colon, that is a reflection of the global namespace. This is really one of the cases where you need to refer to the global namespace all by itself, not just as a prefix for a qualified name. You reflect other namespaces. So caret std chrono is a reflection of the namespace std chrono. Caret std fopen is a reflection of the function fopen. And you can take the reflection of a compile time expression. Barrier max is a const expr function. So this is a compile time expression. It'll take the reflection of that. Actually, it'll take the reflection of the computed value of that compile time expression, not the details of the expression itself. Okay, about the syntax of the caret operator. There's been
Wait, so what happens if the thing that you're referring to is ambiguous? That could be a local variable, could be a global function. What has it determined?
Probably fails with a compilation error. Yeah.
So in the case of an alias, you don't see through the alias to effectively compute the type. But in the case of an expression, you do compute the value. Is there any thought on the reasoning behind that?
The alias, keeping the alias and not immediately going through it is because they are interesting in their own right. An alias is a member of a scope. And so if you go through the scope, you want to be able to find it. So the expression, that's possible. The reflection of expressions is an area that's probably still being developed. You can't reflect inside an expression or any details about it. So if you want to do that, then yes, that can probably change. But right, yeah.
Can you reflect inside a reflection expression? Like for the parentheses barrier, could you have another caret percentage and get the reflection of the meta info?
You can, yes, you can. You can't do anything useful with that. Yeah, you can have nested carets. You can have a double caret. It's legal. It's not useful.
Sorry, I have a question. Why do we make this const x? For example, if I have a function that takes value, there's only regular runtime. So how do so the function itself is not like const x, but
you
use the reflection mechanism?
Well, if you were trying to take a reflection of an expression, it has to be a compile time expression. You can't take the reflection of a runtime expression. That's just not allowed right now.
But the decal type would be okay.
You can, right? That's a type. If you do a decal type of some expression, that is a type, and you are allowed to reflect any type.
What happens if that's a dependent expression? Like imagine this barrier of t and like t was a template parameter.
Well, that would be evaluated when the template is instantiated.
I see.
So yes, it would be a dependent. X would be variable with a dependent value that you can't instantiate in the prototype template. It has to wait for template instantiation to fully evaluate it or do anything with it, like any other expression. Okay. There has been an objection to using the caret for the reflection operator because the caret is already used by Objective-C and Objective-C++. There is concern that users and maybe even compilers will be confused about which language the caret is supposed to represent. Because remember, in Objective-C++, you can have regular C++ in there too. So in Objective-C++, a caret would be used in both contexts. It is not known yet if this objection will be strong enough to force a change to the proposal. If the prefix character operator is nixed, some possible replacements would be to revive the reflexper keyword or use the at character or a backslash, because the at character was recently added to the basic character set. So it is now available as C++.
Well, couldn't people get confused that it's Java?
You are less likely to mix C++ and Java in the same source file. But yes, there's probably other people who want to use at for something else, so may not go there. So
What's the order of operations?
the what?
Or the order of operations with the caret?
The caret is a regular. It has the same precedence as other prefix unary operators.
What happens if I take a reflection of a function of an overloaded functional operator.
That I believe that is currently a compile time error to try to reflect on an overload set. The authors are working on how to deal with overloads and overload sets. So that's an active area of research. So what'd you say?
That could be a future extension.
Yes. Yes. Okay. So if the syntax for the reflection operator is changed, there will the semantics will remain the same. So it's just the spelling of the operator, and I haven't heard any objections to the semantics of how it works. So to go from the reflection world to the code world, use a splicer, which is a pair of brackets made up of square brackets and colons. The operand inside the brackets must be a compile time expression that is, or that can be implicitly converted to, std meta info. Splicers are hard to describe and are best understood with examples. So here we have the reflection of the built-in type int and store it in the constexpr variable r. Then we splice the reflection variable named r back into the code world. Because r is the reflection of int, the variable x has type int. It is possible to get the reflection of something and immediately splice it back into the code. It is legal, but not particularly useful.
Would auto in this case be std meta info?
Yes, auto, the type of R is std meta info. Because that is always the type that a reflection, that is the type of the reflection operator. You may have noticed the use of type name before each of the splices. The keywords type name and template are sometimes required before a slice operation, similar to how type name and template are required before names that depend on a template parameter. In all these cases, the keywords help the compiler with its syntax parsing. In the example with the template keyword in this slide, the compiler needs to know that the splice of VT is a template, so it knows how to correctly parse the less than operator just after the splice. So exactly when the type name and template keywords are required is still undergoing development, trying to make them required in as few places as possible, but they will be required in some places. A splice can be used almost anywhere that the reflected thing is valid. So here, type is a reflection of the type long, so you can use it anywhere that you can use the type long. Template arguments as a type of a variable or inside the static cast.
Do you not need the type name keyword inside static cast?
No, because the argument of the static cast has to be a type. It can't be anything else. You can take the reflection of a namespace and then use that in a qualifier of a qualified name. You can take the reflection of a function and then use it anywhere that function can be referenced, taking the address of it or calling it in these cases. You can take the reflection of a data member of a class and then use it anywhere that data member can be used. This place. Except I think the implicit this does not work with a spliced data member. So this has to be explicit.
Excuse me. Well, what happens if we take the reflection of small a?
Yes, what if you take the reflection of small a?
It's not a
That is a local variable. It's not a compile time expression, so no, that doesn't work.
Okay, but if A would be like a const expert, for example.
If A were const expert, that should work. I don't know exactly what happens.
Okay. So I'm referring to implicit this in this case, if it would be possible to yeah. Okay.
So here, member is referring to the Z inside the struct A, right? So
Yes.
Any other struct with a member named Z could not use that.
Right. The reflection refers specifically to the Z inside of struct A, because that's what we reflected. It won't go looking for some other thing named Z. Up next, we'll discuss the meta functions in the proposal. They are all const eval functions in the std meta namespace. The parameters are generally reflection values of type std meta info. The return type is appropriate for whatever was asked for, which is often a Boolean, a meta info, or a vector of meta info. 1.2 note, which I forgot to put in the slide. Reflection values are always of type std meta info, which is of course in the std meta namespace. All the functions that operate on infos, on reflections, are in the std meta namespace. So argument dependent lookup works in this case. When calling one of these meta functions, you normally don't need to specify the std meta namespace. ADL will find the right function. I won't go over all the meta functions because there are too many, but I will cover different groups so you can get a good sense of what they can do. So first we have the meta functions that tell you what kind of reflection you have. You say, is this a type? Is this a function? Is this a namespace? And a bunch of other things. There's one for dealing with names. Anything that has a name, you can ask what its name is in several different forms. You can also ask for its source location. It'll give you back that C++20 source location object type. So you can assign what file and line number this thing was declared at, if there is such information, if that's meaningful. Many of the meta functions duplicate what you can do with type traits. So you can ask for what kind of type it is, integral, array, class, function type. You can ask for all the properties and the relationships between types. Are they the same? Are they convertible?
Not sure if I missed this, but why are they methods instead of free functions?
Lots of people are much preferring free functions these days for various reasons. I don't know all of them. But yes, all these functions are free functions. Std meta info is a scalar type. It does not have any.
Oh, that's why.
Yeah, okay. It's an opaque scalar type, but it is scalar.
So now that we have chosen to use one universal type meta info, it's possible to make a construct which makes no sense in the problem domain, that is not through default constructible of a meta info of a global namespace. What will happen then? Right.
So you ask, what happens if you do a nonsensical query? If you ask, right, is this an enum type for a reflection of a namespace? Doesn't make sense. You will get a compile time error, and at least in the current implementations, it will say, right, that this cannot be a constant expression. And sometimes it will explain why, and give you a good error message. Yes, but if anything that's nonsensical, you will get a compile time error.
If you had a vector of heterogeneous
reflections, you don't know until you ask it questions about it. So if you ask it, is it an enum and it's not, why would that be an error?
Actually, I'm not sure exactly what the I don't for these is functions, these Boolean, is it something, is it this kind of type? Is it a function type? I don't know what happens if you feed it something that's not a function. Sorry, if you feed it something that's not a type. It could return false because yes, this is obviously not a function type. Or it could give a compile time error. I'm not sure which. There definitely are some where, right, if you ask for all the non-static data members of a class, if the reflection you give it is not a class, then yes, in that case I definitely know it will give you a compile time error. So yes, there can be debates about exactly what the input range is for these functions, where you get a compile time error or where you can return a useful empty set or whatever. I don't know where all those details are, and that can probably be debated. But yes, nonsensical things do get you compile time errors. These meta functions, you can do things that you cannot do with type traits. You can ask if it's a class member, you can ask if it's public, protected, or private. You can ask what this symbol's linkage is. You can ask about the virtual modifiers on member functions and some other properties that are invisible to the existing type traits.
What happens if a property changes during compilation? Like, let's say class is forward declared, you don't know if it's trivial, and then later you know it's trivial, or something like that.
People have thought of that. I don't know what the answer is. I think they would like to make it a compile, an error of some sort. But maybe it's an error to ask if an incomplete class is trivial. Yeah, there might be requirements that these classes be complete. So, but yes, the problem of a class, incomplete class later becoming complete is one that plagues large parts of the things. And yes, the people working on this are aware of it. I just don't know exactly how it has been resolved.
So the previous question suggested to store meta-info instances like in a vector. Would it be possible then to iterate?
Yes, you will see that. You can iterate them over them at compile time.
Okay, cool.
This basically requires the context per vector,
okay,
which has been really hard to implement, but people have it now. It is available now. So you can have, so some of these meta functions return a vector of info,
okay,
which you can iterate over at compile time. We'll have examples of creating vectors of info at compile time, iteratively. So, you can get the members of things. Members of works on classes and namespaces. And you can apply filters, which I won't explain in detail. You can apply filters so you get just the kinds of members that you want. That's possible. And for classes, you can get the basis, static data members, non-static data members. Subobjects is basis and non-static data members. You can get the enumerators within an enum. And ones I find quite intriguing for templates. If you have a reflection, you can ask, does this have template arguments? Is it a specialization of some template of some sort? And if it is, you can get what's the template that was specialized, and what are the template arguments. So you can.
Can you tell if it's an explicit specialization?
No, I don't. I'm pretty sure the answer is no. But if then you look inside that class, that type, you will see the members of that explicit specialization rather than of the general one.
if you were to reflect an instantiation of make index sequence, would template of give you make index sequence or index sequence or integer sequence?
I'm not sure. I'm not sure which or which. I don't remember the details. It would probably. It is a template, one that's actually used. Yes, it wouldn't be a reflection of the function, but if there is one, I don't remember the details of how it works. But it would probably be a reflection. I'm guessing it would be a reflection of the type alias, of the templated alias. He asked about make integer sequence and what do you actually get when you do template of. There's some more features in the reflection proposal still to be covered, but we've covered enough that it is time for some real examples. But before doing that, we need to take a short detour. For compile time reflection to be really useful, there must be a way to loop over a collection at compile time. And no, a regular for loop inside a constexpr function isn't good enough. There is a standards proposal to add constexpr loops to the language, referring to them as expansion statements. The proposal seems to have stalled, but it is so useful to reflection that P2996 and the slides in this presentation are written assuming expansion statements exist. When you see what looks like a range space for loop with template in front of it, read that as a loop that is expanded and unrolled at compile time. Most compilers don't implement expansion statements yet, so a workaround is available. The syntax is rather ugly, but the effect is similar. The template for syntax will be used on these slides, but the expand syntax will be used in all the compiler explorer links so that the code will actually compile. Oh, you may have noticed there's compiler explorer links and occasionally some other links down there in the bottom. I don't expect you to read them or copy them now. They will be clickable links on the slides that will be posted after this. So one final look at our size or length problem. Use the reflection operator to get a reflection of the template parameter type. Then use a couple of the meta functions to get a collection, which in this case is a vector of info, to get a collection of the member functions within the class. So we called members of, but we asked for only members that are functions. Iterate over those member functions. When we find one named size or length, call the function using the splice operation to generate the correct code from the reflection. One other thing to note, we can do a slice inside a requires expression. At least I think we can. The compilers are getting an internal error on that right now. That makes it easy to check that the member function not only has the right name, but is callable in the way that we want to call it. The next example is one of the things people most want from a reflection, converting an enumerator to a string. This is relatively simple to do with reflection. Get the reflections of all the numerators of the enum type. Iterate over them. If the value of one of the enumerators matches the value we are looking for, return the name of that enumerator. If your coding philosophy is to avoid all raw loops, including range-based for loops, then you can write the same code using ranges and std map. I won't go through this in detail, but you can hopefully see that reflection-based programming looks a lot like regular programming. Now back to the very beginning of the talk, where I hopefully piqued your interest with the magical parse options function. this is how the magic works. The type that holds all the configuration options is specified as an explicit template parameter. Iterate over all the static data members of that type. Search through all the command line arguments, looking for one that matches the name of the non-static data member with a double dash in front. If the parameter is of type bool, that's easy to process. Otherwise, we use IO streams to parse the value of the argument for the option. Throw in a little bit of error checking, and we have a decent generic command line parser. One thing to note here, we iterate over the members of the struct that we want to find the options for. In most command line parsers, you iterate over the command line options, looking for ones that match the strings that you're looking for. So we flip this, but do the same thing. Okay, there are a few functions in P2996 that are worth calling out because they are not like the others. Splicers behave as if they insert the thing being reflected directly into the source code, and then the compiler compiles the code as if the thing being reflected had always been there. But the functions substitute and define class change the state of the compiler without injecting any actual code that is compiled. The function substitute performs a template substitution. The inputs are a reflection of a template and a span of the reflection of all the template arguments. And the output is a reflection of the type that was created.
Could you have written just this thing digitally instead?
The substitute function combines the template and the template arguments into a type, kind of like the line at the bottom, except that you can't do it that way because arg is not a pack that can be expanded. So it behaves kind of like the line at the bottom, but you can't do the line at the bottom.
Can you reflect on a pack?
No. Currently, no. That will be fixed at some point. But packs introduce a bunch of thorny problems. Where am I? So, an example of substitute. I got this crazy idea that, say we have a container that's allocator aware, and we want the value type of that container to use the same allocator where possible, where that's feasible or reasonable. So if the value type, if the template parameter that specifies the value type for a container, if it's also allocator aware, and it's using std allocator, which means they probably didn't worry about the allocator, but our container is using some custom allocator, we want to replace the value, we want to replace the allocator in the value type so that the allocator of the container and of the value type match. I don't know if this is a good idea, but now with reflection, we can actually do it. So we can start to think, is this a good idea? But anyway, it's an example of substitute. So this is how we can accomplish that. Iterator, I know this is hard to understand. It was a little challenging for me to write. Iterate over the template arguments of the value type that was given to the container. If the template argument is a specialization of std allocator, so we get the template of, compare it to std allocator. So if this is a specialization of std allocator, replace it with a specialization of the desired allocator. The allocator traits rebind is necessary because the template arguments for the two instances of the allocator are different. But this is tricky. We've got the various reflection operators and splicing operations. But I'm somewhat confident that it does what it's actually supposed to do. So once all the necessary adjustments to the template arguments have been made, the new value type is created by calling substitute. So we walked through the template arguments of some type, possibly adjusted some of them, made changes to some of them, and gathered them up, and then used that new set of template arguments with the adjustments to instantiate or to specialize the same template, but with the new template arguments. And this is how change allocator would be used. In the definition of the container, we set the value type alias, to the result of calling change allocator. While substitute will create template substitutions out of reflection values, define class will, as its name implies, define a class using only reflection values. It doesn't create the class entirely out of thin air. One of the inputs is the reflection of an incomplete class, which must have already been declared. For now, only non-static data members are supported because they have the best combination of being both useful and easy to implement. Other kinds of members will come along later. The data members that define class should create are specified with the reflection of the type of the data member and a struct containing other settings. Only the type is required. Everything else, including the name, is optional. The function data member spec is used to create the reflection of the data member that define class needs. So this is a somewhat complicated API. Be nice if this were simpler, but it gets the job done. I'm not sure how to make it simpler while still giving all the functionality that you would want. So here's a very simple example taken from the paper. The code at the top behaves the same as the code at the bottom. Note that calling define class with a template specialization that hasn't been fully instantiated yet behaves the same as an explicit specialization of the class template.
So this modifies the class definition itself, so I don't need to
It defines the class. There has to be no class definition up to this point. So simply doing the reflection of S of int, that does a substitution. It doesn't do the full instantiation yet, so S of int isn't fully defined yet.
I don't need the return value of defined class.
It can be useful.
It needs to be something that is valid at namespace scope, right?
What needs to be valid at namespace scope?
Or can you, I mean, if you're putting it directly at namespace scope, which a direct function call would not.
Well, no, the class that's being defined has to have already been declared.
Yes.
It has to be an incomplete type. So it already has to be a class, either a non-template class or a template specialization that hasn't been fully instantiated yet. So those already have to be at a valid scope. You just asked the return value of define class, I guess is not exactly necessary. You can always get to this class by calling it S of int, but there are definitely cases where it's useful to have the reflection of the just defined class there because you're going to do other things with it.
So it acts like a type def at this point, or?
But it defines the class.
Yes.
It actually provides the definition for the class.
What happens if I call define class in two distinct namespaces for the same type, S of int?
I'm not sure. I haven't tested it. I don't remember reading it. I assume if you call define class twice on the same type, it'll be an error.
Yeah, but in different namespaces.
No, but you have to give it.
Okay.
You have to give it an incomplete class,
Yes.
and that only lives in one namespace. And what's returned by defined class is a reflection. It's not the class itself. It's a reflection of that class.
So basically, we will have like large scale code, and someone defines like align 64, and someone else defines align 8, and we get a bunch of errors. Like magically.
That's possible. I'm guessing. We don't have enough experience with it on large scale to know how that's. But yes, that had occurred to me that you have to be careful how you use define class so you don't accidentally call it twice on the same type.
Okay.
So is the thing that define class returns always the same as the first argument, or is it transformed in any way?
No, it is. Nope, it is.
It's always exactly.
Well, except before calling define class, the first argument was a reflection of an incomplete type. And what it returns is now a reflection of a complete type.
Okay,
it's the same type, but it's now complete.
So if I have it as, say, a const expert variable instead of a direct parameter, would that variable be equal to return type afterwards? That is, does calling define class alter the behavior of the argument?
The reflection, so you're asking, is the reflection you pass in the same as the reflection that it returns?
Yes.
I don't know. It's quite possible that it is. I don't know if a reflection changes it. Right. You take a reflection of an incomplete class, then you define it normally.
Yeah. So
and then take the reflection again of that same class. I don't know if those two reflections will compare equal. I don't know if the completeness of the class is part of the value of the reflection. That's a detail I don't know. Sorry. And that would affect whether the parameter and the return value are equal.
So I guess reflections, if I had a reflection without the defined class and I'm reflecting over a template instantiation, the instantiation won't actually happen as far as the compiler is concerned.
Right. Taking the reflection of a template specialization is not enough to instantiate that class. But it will, you can then splice that reflection later and use it in a way that will cause it to be fully instantiated.
Can you still define the primary template after defining a specialization through this?
Yes.
But you can't do it before.
No, you could do it before. I believe
it has to be an incomplete type.
The specialization is still incomplete, even if the template has been defined. The template specialization becomes complete when you do the full instantiation.
Can you check that it's incomplete before defining it? Can you do if const expert is incomplete? Define class else.
I would hope so. I don't know how that's done. If it's not in the reflection, it stally will be at some point. Because yes, the incompleteness is a useful thing to know. Here's an example that could be very useful for developers in the high performance space. Even though an array of structs is more readable and more maintainable, a struct of arrays often has better performance due to increased vectorization and caching effects. In many applications, data structures will be manually changed to use struct of arrays. Well, now with reflection, that change doesn't have to be done manually. Given any struct whose data members are scalar types, a new struct with corresponding members that are arrays instead of scalars can be automatically created. To do that, iterate over the data members of the given type. Create a new data member that has the same name as the old data member, but whose type is a stood array of the old type and the desired size. Use define class to define a new type with the new data members. The implementation may look a little complicated, but the use of this is very simple. And that's one of the goals of software engineering, to make things easy for the end user. It would be even nicer and easier to use if the struct of arrays class came with member functions that made it look like an array of structs. But that'll have to wait until define class can define member functions and not just data members. You may be saying this all looks great, but even if this makes it into C++26, it will be at least several years before I can try it out. Wrong. There are already 3 implementations, well, 2.5 implementations, available on Compiler Explorer. But be warned that all these implementations are preliminary. They have plenty of bugs and unimplemented features. So please don't use reflection in production code just yet. But please do try this out and play with it and give feedback to the paper authors. EDG, Edison Design Group, we make C++ front end that's used in some compilers. They were the first, an EDG employee, David, is the lead on P2996. So they had the first implementation of this paper. It's a hidden option in the EDG front end, available on Compiler Explorer. That's the compiler you want to select to try it out. Someone, unfortunately I forget who, did a fork of Clang that implemented this. That's also available on Compiler Explorer. Choose that compiler. That one has P2996 in its name. And then the NVIDIA HPC C++ compiler, NVC++, that I'm the lead on. Our latest, it is based on, we use the EDG front end, so our latest release has this reflection in there. It's available on Compiler Explorer. Because this is a regular production release compiler, you need to specify these options. You specify the reflection option, you need to put it in C++23 mode, because the reflection is not on by default. Because it's a production compiler, this is also available for download. You can run it on Linux for free. So if you want to try out reflection in something bigger, and try it out, don't put it in production code, but if you want to try it out on some bigger application, you think this part of it could benefit from reflection, please download the HPC SDK and give it a go. So I have one more example on how reflection can solve real-world coding problems. Automatic serialization. There are some very good serialization libraries out there. They have powerful features and can handle most things automatically. But one important feature can't be done automatically. Serialization frameworks don't know what to do with classes. In existing libraries, there is no practical way to peer inside a class to see what needs to be serialized. So users are required to supply a function that tells the library how to serialize the class. The introductory tutorial for Boost serialization contains this example. To serialize class GPS position, the user needs to write a function named serialize with the right signature. This big hole in automatic serialization can be filled in by reflection. The serialization code can use reflection to look at all the class members and make reasonable decisions about how to serialize them. To demonstrate this point, I wrote a very small and basic serialization class. The goal of this is to show how reflection can be useful. It was not my goal was not the goal to be a top-notch serialization library. There's a lot of boilerplate code to handle non-class types. This code doesn't need reflection, so it's not very interesting. This is all the serialization code. There is similar code for deserialization, but doing everything in reverse. Now for the interesting part. This is the code to automatically serialize a class or a struct. Iterate over the base classes, serializing each one. We get the base object using a static cast because base class objects don't have names. Then iterate all the data members and serialize each one using a splice of the reflection of the data member to access it by name. When I started on this serialization example, I was expecting there to be more reflection-related code. I was pleasantly surprised, however, by how powerful reflection is and how easy it is to do things that used to be impossible. The code to deserialize a class or struct is very similar, except that bit fields complicated things a little bit. It is not possible to take the address of a bit field or create an L value reference to a bit field. So we have to deserialize into a regular variable. We make sure it's of the right type, and then assign that to the bit field. So what can we learn from this small example? So reflection about serialization from this example. Reflection can handle many classes automatically, but not quite all of them. Here are some of the problem areas. It doesn't do non-public data members because the access is done by regular access checking. But that can be worked around by making your class saying that serialization is a friend of your class. Just put that friend declaration inside your class, and the serialization code, but no one else, can access the private data members to serialize them. Pointers are, of course, a problem, but a really smart serialization framework can handle some of those cases by then serializing what it points to and can, in theory, serialize a whole tree, a whole data structure. Three in the middle are the harder ones. References. It's not clear how you would serialize a reference, or more probably, you don't know how to deserialize it. You can't say unions. Serializing them, the serialization code does not know what the active member is. There's no way for it to know that automatically. Something else, some other information in the class has to tell someone what the active member is. And then for simple deserialization to work, the members have to be assignable. They're not, the deserialization can work fine, but getting it back will run into problems. So the real conclusion is, even though reflection can help in a lot of cases, a good serialization framework will still need, at least to allow for users to control how a class is serialized, even though it should no longer require users to specify that. There's enough confidence in the success of P2996 that some papers are already being written based on it. I'll mention two of them here. P1240 included reflection of function parameters. P2996 dropped that support, partly due to the problem of parameter names. Different declarations of the same function can have different parameter names, so it's not always clear what name reflection should return. P3096 argues that reflection of parameter names is very useful and important, and it should happen now. And it goes over the possibilities for what name to reflect and makes an argument for which one it thinks is the best choice. So it's both advocating, say, we need to do this now, and second saying, here's how we think it should be done. So it is helping advance the work. The only kind of members supported by defined class is non-static data members. Support for other kinds of parameters is listed as a future direction in P2996. Andrei Alexandrescu in P3157 makes the case that member functions should be supported sooner rather than later. The hardest part of defining functions is how to specify the function body. Andrei proposes the intriguing idea of defining the function body with the reflection of a lambda with the appropriate signature. That shows promise, in my opinion, but there are still lots of details to be worked out. I don't think P3157 will get folded into P2996. That would go against the minimal viable proposal goal. But it is good that people are working on follow-on features while P2996 is still being developed. That will shorten the time until a feature-complete reflection facility is available. And if we really want to see the future of reflection and get a glimpse, see the full power of reflection and get a glimpse of its future, go back in time 7 years and watch Herb Sutter's CppCon keynote about meta-classes. The details have changed a lot since then, but the idea of taking code injection to the extreme is still worth considering and pursuing. And if you're interested in reflection, it's very interesting. So other talks about reflection. On Wednesday in Flug, here at this conference at 11 o'clock, Saksham Sharma will be talking about reflection is good for code health. There'll be some overlap with this talk, but hopefully not too much. And Inbal was supposed to present Welcome to the Metaverse here at this conference, but she had to cancel. She was unable to attend at sort of the last minute. But she gave this talk a couple weeks ago at ACCU as a keynote. So if you're interested in this area, watch that once it becomes available online. So final conclusions. What I hope you will take away from this presentation. C++ reflection is coming. There's a good chance that it will be in C++26, but even if it misses that, it will be in the standard before too long. C++ reflection happens at compile time. If you want to use reflection, you should up your compile time programming game. But you don't need to master template metaprogramming, since reflection is based on non-template constant val functions. C++ reflection is good at reducing the amount of boilerplate code, making it possible to do generically what currently has to be done manually and repetitively. There is still lots of work to do. If you're interested in reflection, please try it out. Connect with others who are also interested. Give your opinions and suggestions, and pitch in however you can be most useful. Thank you.
In the proposal you mentioned that's an extension of the define class. Does it allow you to name member methods that are operators?
Yeah, asked in the Andre's proposal to extend define class to handle functions. He asked if it handles overloaded operators. Yes, at least mostly the basic ones. The name can be operator plus or whatever. And so, right, if your operator looks like a normal function, then yes, it should handle it. Constructors are he's still figuring that out. Those are harder.
What's really exciting is being able to just inherit from a class and then have introspect what CRTP like on steroids, and it'll just look down what it inherited and inject all those into this lower class would be crazy.
Yes, good point. So he said inheriting from a class and then using reflection could be like CTRP on steroids. So yes, you could write functions that look at your base classes and look for any interesting things and create functions in your derived class that do whatever they want to manipulate the base class. Yes, those are use cases that have been thought of that we want to be able to do.
Yeah, I'm sorry if I missed this, but the restriction to define class, you have to have an existing incomplete type. Is there a reason why it can't just create classes?
I'm sure David has a good reason. I don't know what it is.
Okay.
Sorry.
If someone else knows, I'd love to talk about it.
So The main thing I think would be that it has to have a name in the outer scope somehow. And having an incomplete type is the easiest way to do that. I mean, I guess you could have inside a function, you could have declare a local incomplete type and then define that.
Yeah.
And return it.
You had that one function that later on in the slide you said this was like if we could do, this template of, dot. Was there a reason they just wouldn't allow that other?
Well, in that case, that was right how the substitute function works. The arguments are not a pack, and I don't know that there's an easy way to get them to be a pack that you can expand with the dot.
If you had a template parameter pack of, or a non-type template parameter pack of meta info, couldn't you use that syntax?
Maybe. Explore that, see.
How do you debug this?
Yes, how do you debug this? The same way that you debug const expert functions these days. or deep template instantiations. You don't. Okay. Thank you all for coming again.